Natural language processing, NLP, is a field of AI that gives computers the ability to understand, process, and generate human language. It's what allows machines to read text, hear speech, and interpret its meaning, much like we do. NLP powers everything from virtual assistants like Siri to tools that automatically summarize long documents. Next, we will explore how these principles are applied in Azure AI services. Text and speech conversion. NLP allows for converting spoken language into written text, speech to text, and vice versa, text to speech. A common example is generating subtitles for videos. Language translation. NLP powers machine translation, which automatically translates text from one language to another. A classic example is translating a document from English to Japanese. Text classification. This use case involves categorizing text into predefined labels. A typical application is a spam filter that classifies an email as either spam or not spam. Information extraction. NLP can be used for entity extraction, which means identifying and pulling out specific information like keywords, names, dates, or locations from a document. Question answering. This involves providing a direct answer to a user's question from a given text or knowledge base, such as answering, "What is the capital of France?" Text summarization. NLP can automatically create a concise summary of a longer document. For instance, it can generate a short paragraph to summarize a multi-page article. Let's explore how this works. Tokenization is a fundamental and crucial first step in natural language processing NLP. It is the process of breaking down a continuous stream of text into smaller, meaningful units called tokens. Think of it as the NLP equivalent of dissecting a sentence to understand its components. Once we have our tokens, we need to clean them up. We do this in a few ways. Text normalization. We make sure a computer treats run in uppercase and run in lowercase as the same word. Stop word removal. We get rid of common, less important words like the or a. They're great for grammar, but they don't usually add much to the meaning. Stemming. We reduce words to their root, so running and runs are both seen as run. This helps simplify the vocabulary for the computer. Ngrams, bigrams. While stemming split New York City into individual separate words, a bigram model would capture New York as a single phrase, preserving its meaning as a location. Now that we've seen how tokenization breaks down text into individual words, let's look at how we can use statistical techniques to make sense of those words and the relationships between them. These methods move us beyond simple word counting to understand the structure and meaning of language. When it comes to analyzing text, two essential statistical methods you need to know are naive Bayes and TF-IDF. Naive Bayes is a simple and fast way for computers to categorize text, like sorting emails into spam and not spam. It works by learning from examples. It counts which words appear most often in spam emails, like free money, prize winner, or urgent claim, and which words appear in regular emails. When a new email arrives, the model looks at the words inside and uses those counts to predict if it's spam or not. This approach is called a bag of words because it only cares about which words are present, not their order or position in the sentence. Term frequency inverse document frequency, or TF-IDF, is a way for a computer to figure out how important a word is to a specific document. It helps a machine prioritize unique and meaningful words over common ones. TF-IDF is based on two key ideas. Term frequency, TF. This is simple. How often a word appears in a single document? If a word like apple shows up many times in a document about fruit, it's likely very relevant to that document's topic. Inverse document frequency, IDF. This is a bit more clever. It measures how rare a word is across a whole collection of documents. Common words like the or and appear everywhere, so they don't help us distinguish one document from another. TF-IDF gives these common words a low score. On the other hand, A rare word like photosynthesis would have a high IDF score because it is very specific. The final TF-IDF score is calculated by multiplying these two values together. A word gets a high score if it appears frequently in one document, high TF, but rarely in all other documents, high IDF. This is how a machine can identify the most unique and important words in a text. Let's transition to semantic language models. These advanced models move beyond simple statistics to understand the true meaning and context of language. As natural language processing has evolved, the focus has shifted from simple word counting to a deeper understanding of meaning and context. This is all thanks to a concept called embeddings. What are embeddings? An embedding is a way of representing words or tokens as vectors, which are just lists of numbers. These numbers give a word a position in a multidimensional space. The key idea is that words with similar meanings are placed close to each other in this space. Think of it like this. If you plot words on a map, words like king, queen, and prince would all be clustered together because they're related. A word like table would be far away in a completely different area of the map. This is exactly what an embedding does, but in many more dimensions. The closer two words are in this word space, the more similar their meanings are. Modern language models use these principles to create powerful AI. They train on vast amounts of text to learn the relationships between words and then use these embeddings to perform a wide variety of tasks, from translation to generating new text. Let's explore how machine learning classifies text. To train the model, you give it examples of text that are already labeled. For instance, you would show it a review like, "The food was great," and label it as positive. You would also show it "slow service" and label it as negative. The model then learns to associate certain words with a specific sentiment. Words like great and tasty are linked to a positive label, while words like terrible and slow are linked to a negative one. Once the model is trained, it can analyze new unlabeled text and predict its sentiment. To summarize, NLP gives computers the ability to process human language through a series of steps, from tokenization to the use of statistical and semantic models. These techniques are transforming industries by powering applications like language translation and text classification. Next, we will explore how these principles are applied in Azure AI services.